Okay, so now we're going to talk about addresses, cookie token addresses, or Bitcoin addresses, if you will. Addresses can look like this, as you see on the screen here. It starts with a legacy, a very common address format is the one you see here, which starts with a 1, and then you have a lot of different numbers. I will talk about this today. I will explain what addresses are used for and how they are constructed and why they are needed. So addresses are used to send money from one person to another. If I want to receive money from John, I will give John my address, and he will pay, and then he can pay money to my address. Okay, but let's look at a specific problem with this cookie token spreadsheet right now. We have extremely bad privacy in this spreadsheet because everyone's name is literally in the spreadsheet. So for Chloe, for example, here it says anyone who's looking at this spreadsheet can figure out that Chloe buys a lot of cookies. And this might be very interesting information for, I don't know, insurance companies or other people, governments maybe. So people are, this is just horrible privacy. No one wants to show to the whole world how they spend their money, how much and to whom. So this is really bad, and we want to get rid of this problem. So to help privacy, we will replace the names with their corresponding public keys instead. So instead of the cafe's name here, we put cafe's public key here. And instead of Alice's name here, we will use Alice's public key over here. So this is how we're going to transform this spreadsheet. And when we have done this, you can see that it's not as obvious who is who in this spreadsheet. You don't know who Alice is, or even if Alice has done anything in this spreadsheet. So we're going to replace the names with public keys in the spreadsheet to preserve privacy or to improve privacy for users. And a typical payment would from now on look like this, just as before. Suppose that the company wants to pay 100 cookie tokens to Faisa. Faisa is a new employee. She hasn't used this cookie token spreadsheet yet. So Faisa is new, and she wants to receive a gift from the company, for a welcome gift for 100 cookie tokens. So what happens then? It means Faisa will, in order to receive those 100 cookie tokens, she would need a private key and a public key. So she creates a private key and her public key, but she doesn't send the public key to Lisa anymore. So she keeps Lisa isn't interested in her public key anymore, but she instead sends this public key to the company, the payer, the one who wants to pay money to Faisa. Okay, so he creates his key pair and gives the public key to Faisa and says, gives the public key to the company and says, okay, here's my public key. Please pay 100 cookie tokens to this public key. And then the company creates a message like this, an email to Lisa just as before, but it's going to be a bit different. And the message says, Lisa, please move 100 cookie tokens to Faisa's public key and send those 100 cookie tokens from the company's public key. So there are no names in the message anymore. So Lisa doesn't know who this is really. So Lisa can just see that, okay, I'm about to send money from one public key to another public key. And this message is also then signed here by the company's private key. And the signature is attached to the signature, to the email, like before. Okay, so there are no names anymore in these messages, just public keys and signatures. And this message is sent to Lisa, who will verify it. She will verify this message here with verify that this signature signs this message for the sender's public key. So the input to the verification is the sender's public key, the message, and the signature. That's the three inputs. And suppose now that this is okay, then Lisa can check the balance of this public key, 037 and so forth. And if the company has the if the company has the money to spend, she will execute this payment and put it in the spreadsheet like this. So from company's public key to Pfizer's public keys, 100 cookie tokens. Now, she doesn't know who any of these are necessarily. She doesn't care even. I mean, she's happy she doesn't have to keep track of everyone's public key anymore. She just does this without knowing who's who. So this is the new payment system. And no one has to reveal their names anymore, to Lisa at least. So, okay, so we have this system with public keys, but there's one slight problem here. It's that the public keys are pretty long. They are usually 33 bytes long. So is there a way to make this shorter without losing security too much security? Yeah, we can do that. We can shorten the public keys. So in the spreadsheet where we used to have public keys, we can replace them by their respective public key hashes, as they are called, which is just a hash of the public keys. So we'll see how this works here. This is how we would do that. So let's have a look at John's public key, which is 33 bytes. If we hash it with SHA-256 and then hash that result with RIPE-MD160, you will get a 20 byte result, or 160 bytes. RIPE-MD160 is just another cryptographic hash function. It works differently from SHA-256 internally, but the properties are the same as for SHA-256. So it's this hash function also has these important properties of a cryptographic hash function. So in this process, we shorten the public keys from 33 bytes down to 20 bytes, which is a pretty good win, which means that the spreadsheets can be a bit smaller, doesn't take as much space. And to do that, we need to adjust the payments process a little bit. So the message will, the recipient of the message of the payment will now not be a public key, but a public key hash. So this is, I think this is John paying 10 cookie tokens to the cafe. So he writes, Lisa, please move 10 cookie tokens to public key hash 87E3 and so on, which is the cafe's public key hash. And he still uses his full public key as the sender. And this is signed just as before And then on the verification side, where Lisa verifies this payment, she will verify this message and the signature against this message here using the public key, just as before. There's no difference there. But in order to check whether John has the balance needed to send 10 cookie tokens, she will have to hash this public key, the sender's public key, through SHA-256 plus RIPE-MD160 to get this 20-byte public key hash. And then she can use this public key hash to verify that the sender has the money, and then update the spreadsheet with a new row. So I'm going to go back here, and you might want to ask the question, why do we use two cryptographic hash functions here? Why do we use first SHA-256 and then RIPE-MD160? That doesn't seem necessary. You should just as well be able to use only this function. So you put the public key into RIPE-MD160 instead directly. There are different answers to this. One answer is that it's a security measure, that if any of these functions turn out to be not one way, so if a vulnerability in any of these algorithms is found, the full public key hash, the other one is still probably not vulnerable. So if RIPE-MD160 turns out to be bad, and you could go backwards from this hash to this value here, then you are still protecting the public key from being revealed at this point. But on the other hand, using two cryptographic hash functions can also make it more insecure, because if it turns out that the output set is not as big as you might expect, I mean, you expect from this cryptographic hash function, you expect it to be a random number in the full 160-bit space. But if it turns out that this cryptographic hash function only has 5 possible outputs, to take an extreme, suppose it only has 5 possible outputs, then this full chain of hashes will also be vulnerable. So if either one of these are vulnerable due to a lower output set, then the full chain of hash functions will be equally vulnerable. So it's good in one way and bad in another. This is actually going to be removed later in a future upgrade, which is called Taproot. So in Taproot, we're going to go back to use public keys again. But let's leave that for now, and just accept that right now we are hashing it through SHA-256 and RIPE-MD160 to get a 20-byte hash, and this is the new payment process. Yeah. But there's one problem with this. Suppose that John makes a typing error. He sends a message to Lisa and asks Lisa to move cookie tokens to this public key hash, where the last character is a D instead of a C. So he's making a typo here. What happens then? Lisa, she doesn't care about who the recipient is. She just sees a public key hash here as the recipient. So she will just add that as a recipient here. So there's a row, now there is a row in the spreadsheet with the recipient that doesn't have a corresponding public key. No one can, if we again go back to this here, and suppose that this one here is misspelled, then there is no such public key known, at least, that corresponds to this public key hash. So, and since there is no public key corresponding to this public key hash, then it would mean that there is also no private key corresponding to this public key hash, which means that no one can ever spend this coin. So this is an unspendable output. No one can ever spend it. So this is the equivalent of burning money. And this is bad. You wouldn't want this to happen. So that's when we come up, why we come up with something called addresses. And an address is just a way, it's a checksummed public key hash. So it works like this. You have the John's public key hash up here, and you run it through something called base 58 check encoding, and out comes something called a cookie token address, or a Bitcoin address, if you will. So this is John's public key hash. This is John's address. And we will look closer at this base 58 check encoding, how this works. So when John wants to receive money, he doesn't give the sender this public key hash. He gives the sender his address. That's important. So let's see how he creates his address more closely. From the public key hash, starting at the public key hash, he adds first a version, which is just the version of this address type, so to speak, which is 0. This is the first Bitcoin address that was used in Bitcoin. There are other types of addresses that came later, and there are more types that are coming in the future. But right now, this is the first Bitcoin address, the first type of Bitcoin address. So we have now a versioned public key hash, and then you hash this versioned public key hash and take the first bytes, which will act as a checksum. And then you add this checksum after at the end of the data here to get this versioned and checksummed public key hash. And then you use something called base 58 encoding to encode this data here to get the cookie token address. Base 58 encoding, you can think of it as base 64 encoding, but with fewer characters. Instead of 64 characters, you have 58 characters. But it works slightly different, I guess. But that's the way you can think about it. I haven't put this in the slides, but the interested student can check out the. One moment. Can check out the base 58 algorithm in the book. It's right here. It's figure 51. This is how you go from a versioned and checksummed public key hash to the end result, which is the cookie token address here. And it works, yeah. So this is exactly how it works in Bitcoin too. So I encourage you to read this and try to understand it. And if you do, there are some extra exercises for you later. But this is fun to follow. So I recommend it, but you don't necessarily have to. So this is base 58 encoding. And what I want to say also is that this base 58 check encoding, it goes both ways. You can go from a public key hash to a cookie token address, and you can go from a cookie token address to a public key hash. It goes both ways. This is not a one-way function. So you can decode an address into a public key hash. Okay, so let's see now. When I lost track of the scenario here, but yeah, someone wants to pay money to John. Yeah, so FISA wants to pay money to John here. And what she does is that she asks John for his address, and John will give her that. It's 19G600 and so forth. So when FISA has this address, she will run it through something called base 58 check decode, which is a decoding of this address into a public key hash. We will look into how that is done, and the result is put into the message email to Lisa. This is to prevent typing errors thanks to the checksum. And we'll see how FISA would decode this again. She basically runs base 58 check encoding backwards. So first of all, she base 58 decodes the address. And you can think of that again as base 64 decoding. If there's, that you can move back and forth between base 64 and binary as you please. So you can decode the base 58 string here to get this versioned and checksummed public key hash. And then you remove the checksum to get the versioned public key hash, which you then again hash twice to get the actual checksum. And then you compare them. If they are okay, there are probably no typing errors. There's like 1 in 4 billion chance of a typing error not being detected. So probably not a typing error here. And then you can remove the version and use this public key hash and put it in the message to Lisa in the email. So to summarize, addresses, you can, to summarize, we start by creating a private key using a random number generator. And from that, we generate a public key through a public key derivation. And then we hash this public key through SHA-256 and then RIPE MD160 to get a public key hash. And then we base 58 check encode that hash, that public key hash, into the final address that you can give to a payer. So that was pretty quick too, I think. You can do all exercises of chapter 3 except 3.4, number 4, exercise 4.
So basically, we said that private key is just basically a random number generated from a program, and then we use there's a whole program that goes on to generate the public keys which we share, and then we study about SHA-256, RAPMD, and PCatch. Why is it that you said, if I mean private key is with just me and I'm using it as a signature, but public key is with the other person who can check if this public key is related to this particular private key? How are they able to check this thing? That was one of my concerns. Is there
Yes.
some sort of a program that goes on behind that checks that yes, this is the public key which is related to this private key or something like that?
Yeah, she knows that it's related to the private key because the signature is valid. If the signature is valid here, Lisa knows that this public, the only one who could have produced this signature is the one who has the private key. So
this means that Lisa is checking that this signature belongs to this public key.
yes, belongs to this public key, and thus if it does, she also knows that whoever made this signature had possession of the private key. So if someone steals the private key from John,
then they can generate the signature.
Yeah, they can spend John's money if they have his private key. So, and Lisa, of course, doesn't know John's private key. She only sees the public key and can, but she can be certain that the one who made the signature had the private key. So it's up to John to protect his private key as much as he can.
One last thing, does hashing a particular document or data reduces the size of this particular data? I mean, it does.
Yes, it does. Well, not necessarily reduce it. If you input the word hello, then the output would be bigger than the input. So in that case, the size would be bigger. But for most cases, the size, it reduces the size of the signature.
All right.